Hello statistics students, my name is Emigh, and this video is our discussion on section 3.2, measures of variation. A new term for us. The standard deviation of a set of values is a measure of how much the data values deviate away from the mean. Two symbols that we're going to add to our StatCrunch reference sheet now. Please take that out. If you don't have your StatCrunch reference sheet out, please take that out now. And we're going to add two more symbols to it. The first one here it's sigma. And you may be thinking, oh, we already have the Greek letter sigma. That is the capital sigma like this. Stands for the summation. But this is also sigma right here. How can there be two sigmas? This one's the capital and this one is the lowercase. So the Greek letters, there are capitals and lowercase. So this lowercase sigma is always for the whole semester. It's going to represent the population standard deviation. Lowercase s is going to represent a sample's standard deviation. So we do need to know the difference between them. There's a standard deviation based on the entire population, as well as a standard deviation based on just a sample. Sigma will be for the population, S will be for the sample. New term. The variance is a measure of variation equal to the standard deviation squared. So if we take that lowercase sigma and we square it, this right here would be read sigma squared. That will be our symbol for population variance. And S squared will be our symbol for sample variance. Please add these two to your reference sheet as well. We're going to start to explore standard deviation and variance using technology first. I'm just going to show you using technology how you calculate, how we find standard deviation and variance. After I show you how simple it is to run technology and calculate them, then we will talk more about what they mean. All right, so StatCrunch Chapter 3, if we are asked to find the range, the standard deviation, or the variance from a set of data, then we will click on the light blue rectangular icon. That's going to put our data into StatCrunch for us, like we've seen. We're going to go to that Stat drop-down menu again, and we're going to use the same program that we used in section 3.1. It's the Summary Stat menu, select columns, and then we'll compute. I'll show you how to do that. Let's use this example. Number 1, a class of 10 6th grade students kept record of the amount of time they each spent playing games on the computer during a 1-week period. The times in hours are 11.7 hours, 17.9, and so on, all the way up to one of our 6th graders spent 26.4 hours that week on the computer. We're asked to find the standard deviation and variance for this set of data right here. So we're going to find how far this data deviates from the mean. We'll square that value to get the variance of the data. We're being asked to round our answers to one more decimal place than the original data. We have a second question here. This one is about 10 3rd grade students. This is a younger set of students, typically 3rd graders. They did the same thing, recorded their times right here in hours per week on the computer. And we're asked which class's amount of time on the computer varies more. All right, so we're going to open StatCrunch. It'll look like this when we open that data in StatCrunch. Here we have our 6th grade times. Here we have our 3rd grade times. All right, look at our notes. What do we do next? Stat menu. Notes say to do, summary stats. based off columns again. Here's our program. So we're going to be inputting this data into this program. We'll run it, and then we'll read the output screen. So we are going to, what do our notes say? Select our column by clicking on its name. Question number 1 is about the 6th graders, so we'll click on that. And the other thing we need to look at is what the program's going to provide for us. Variance and standard deviation are here. They're in the default, so those will be on our output screen, so no reason to adjust anything else. So we really just had to click on the column and then compute. Output screen gives us a bit of information, what we're looking for per this question's directions. Standard deviation, 5.7844235. I believe it's asked us to round to 2 decimal places. And then variance, 33.459556. Standard deviation, check out the notation, std.dev, okay? It's the notation that StatCrunch uses for standard deviation, and variance, it writes it out, variance. Okay, so that information for our 6th graders, that was a standard deviation, 5.78, and a variance, 33.46. Okay, it didn't say round to 2 decimals, but it did say round your answer to 1 more decimal place than the original data. Well, the original data was given to us with 1 decimal place of accuracy, so 1 more than that would be 2 decimals. So it didn't say exactly round to 2 decimals, but if you look carefully, it is asking for 2 decimals. So we've got our 2 decimals of accuracy there, and our units. Notice that the variance is squared. That's because we took the standard deviation and we squared it. Okay, let's go ahead and do the same thing for our 3rd graders. When we get back to our spreadsheet, you have the option to just close this and rerun it. But I do want to show you one little shortcut. You can just click right here on Options, and you can go to Edit. If you click on Edit, it'll allow us to choose the 3rd graders instead, and then we hit Compute. So you can do that. Here are our answers. Standard deviation to 2 decimals, 6.66, and variance, 44.39. Another option, if you don't go that route, you can always close it and rerun it. So that was stats, summary stat, columns, choose the 3rd graders, and hit compute. All right, let's put that information back into our notes. For our 3rd graders, that was a standard deviation of 6.66 hours and variance of 6.66 squared, which is 44.39 hours squared. Now we're given a task here, which classes, so that it's either the 6th grade class or the 3rd grade class, amount of time on the computer varies more. So we're going to compare the variance right here for the 6th graders to the variance right here for the 3rd graders. And when we say compare in mathematics, we mean use an inequality like this, check if they're equal, less than, greater than. So for this particular example, it looks like our 6th graders, 33.46 variance, was less than our third graders with a 44.39 variance. So the third grade class's amount of time on the computer varies more. Let's try a few more examples. We're asked to find the standard deviation of these Verizon data speed times in megabits per second. We're asked to round to one more decimal place than the original data. So let's open this in StatCrunch. And that will look like this. Now we go to Stat, our program, Summary Stats. We're running this program based on the columns. We select our column that contains the data we're interested in, and we hit Compute. So we have a standard deviation in megabits per second of 16.45 with 2 decimals of accuracy. Let's put that back into our notes. That would give us a standard deviation equal to 16.45 megabits per second. Part B wants the variance of the above Verizon data speed times to one more decimal place than the original data. So once again, to 2 decimal places. And if we look back on that spreadsheet, output screen to 2 decimal places, that would have squared the original standard deviation for us, giving us 270.76 square megabits per second. Part C wants us to draw a number line and put the mean, which is the 30.74 megabits per second, in the middle of that line, as well as add and subtract standard deviations of 16.45 to and from that mean. Okay, so what's happening now is we're going to start to explore what the standard deviation and variance are. You saw the simplicity when using technology of how to calculate or run the program that gives us the standard deviation and variance. So now let's start to discuss what those values represent. Using a number line is a great visual. We put the mean, because we know the mean is the measure of center. Put that in the middle right here. So we're at 30.74 megabits per second. And we're asked to add and subtract standard deviations of 16.45 to and from that. So if you take your calculator out, you can just use the one on your phone, type in the 30.74, and we're going to first, let's add one standard deviation to that. So you need to hit the plus sign, and then 16.45. If you add a 16.45 to that, we get 47.19, and I want you to put that right here on the number line, and then do it again. Add 16.45 to that. It'll get us to 63.64. Once again, add 16.45 to that, and that gets us to 80.09. So we just added, we took our 30.74, we added to that one standard deviation to get us here. We added it again, so for a total of 2 total standard deviations added to the mean. And then we did it a third time. We added 3 standard deviations to get us here. Now we're going to do the same thing. We're going to take our mean, which is in the middle. This was our X bar. And we're going to subtract 1 standard deviation. So you'll type in 30.74 minus sign 16.45. That'll get us 14.29. Do that again and a third time. And that'll get us negative 2.16 and finally negative 18.61. Okay, so we have the mean, the measure of center. The standard deviation is the measurement of how far we our data is deviating away from the mean. And what we're constructing is a range. Here we have 3 standard deviations above. Here we have 3 standard deviations below the mean. Measure of center, mean. On the next slide, we're going to define what would be considered ordinary data values. Give you a sneak peek. It's going to be everything within 2 standard deviations. And then unusual data values. And that's, just give you a sneak peek, that's going to be any data values further away, more than 2 standard deviations above the mean. And in the other direction as well. Unusual values will be further than that, further than 2 standard deviations below the mean. This right here is going to be our ordinary values. And anything further than that will be unusual. Got a visual on the next slide. Here are ordinary values. That was up 2 standard deviations from the mean and down 2 standard deviations from the mean, creating that ordinary range. And then anything further than that were unusual values. Notice here that we are working with the letter Z. Those are Z-scores. Let's back up a little bit. For many data sets, 95% of the sample values lie within 2 standard deviations of the mean and are considered usual. So these are the usual, the ordinary values. But there's a cutoff, right? There's a maximum usual value, which if we take the mean and add 2 standard deviations, we've hit the max usual value. And if we subtract 2 standard deviations, we reach the minimum usual value. So using our data speed times, that would give us a minimum usual value of, when we had the x's, our 30.74 was here. So that was our mean. We subtracted 2 standard deviations, and that got us down to less 2 standard deviations, negative 2.16. That would be considered the minimum usual value. And in the other direction, we took our mean and we added 2 standard deviations to it, getting us to 63.64, and that number is considered our maximum usual value. When asked, would a data speed time of 60 megabits per second be unusual, we check if it's in this range between the minimum and maximum usual values. And 60 is between these two, so 60 would not be considered unusual. So the answer would be no. 60.0 is within the maximum and minimum usual values, so it would not be unusual to have a data speed time of 60 megabits per second. You can also use our graph from our last slide to see where 60 lies. It would be right about here, 60. So we can see that that is in that usual range here. Anything further than 63.64 or further than negative 2.16 would be considered unusual. These are 2 formulas you might consider adding to your reference sheet. They came from the mean right here, which was x bar. We subtracted 2 standard deviations. That's the formula for the minimum usual. And for this one here, we took our x bar and we added 2 standard deviations to it. That is our formula for our maximum usual value. All right, we're building up to what is called the empirical rule. 68%, 95%. 99.7%. If I were you, I would add these to my StatCrunch reference sheet. You need to remember them. And don't just write those three numbers down, those three percentages. Make sure you put the title, okay? These three percentages explain the empirical rule, okay? Write those down on your StatCrunch reference sheet. And then let's take a look at what the empirical rule looks like graphically. Okay, this right here is called a bell-shaped curve. If we have if we have normally distributed data, it fits into this bell-shaped curve like this. If you just focus on the number line right here, this horizontal axis, just focusing on this, it should look really familiar because this is what we've been building up to, you guys. This number line, we had X bar in the middle, we added 1 standard deviation, then 2, then 3. Headed this direction, we had X bar, we subtracted 1 standard deviation, subtracted 2, subtracted 3. So we've focused on this vertical axis already. Now what's happening? I apologize. We focused on this horizontal axis already. Now what's happening when we go vertically? Well, a dot plot's a nice way to think about it. If we were to start mapping our data values on as a dot plot above the horizontal axis, majority of normally distributed data, which would fill up into this bell-shaped curve, would take place within 1 standard deviation of the mean. You can see that's the highest part of the bell. It turns out, empirical rule, that 68% of the data will lie within 1 standard deviation of the mean. That's 34.13% approximately, plus this other approximately 34.13%. This right here is how we get that empirical rule, which is approximately 68%. That's why we use the number 68 to start describing the empirical rule. Then when we go 2 standard deviations away from the mean, so we're looking at more of these data values, it would fill into this bell-shaped, should it be normally distributed. And if we add all these percentages together, we're going to get 95. 95% of our data with normally distributed data will lie within 2 standard deviations of the mean. That is what we were calling the usual range. If we go an additional standard deviation outside of the mean, so we've got some data values further away. If we go 3 standard deviations out, we have captured approximately 99.7% of that normally distributed data. We're talking about some of the unusually high data values as well as unusually low data values to get us to the 99.7%. Notice there is another 0.3% approximately that we did not account for, and that would be any data values, sometimes called outliers, that would be further away than that. Just a note that the range rule of thumb can be used to approximate the standard deviation. We could just use the maximum data speed time. It was 55.6 if you recall, and the minimum data speed time, that was 14.1 if you recall, or you could just look back a few slides. If we take those max and min values and we do the maximum one minus the minimum one and we divide it by 4, it will give us an approximate standard deviation of our sample data, 10.375 megabits per second. For this particular example, it was not a very good approximation, 10.375, because our calculated one was here 16.45. So it's off by quite a bit, but nonetheless, the range rule of thumb is sometimes used just for a quick approximation of the standard deviation. Sometimes approximation is better than other times. All right, let's talk about that Z. I circled it. I said we would talk about it in a bit. What is that Z? Section 3.3 is on measures of relative standing and box plots. The Z-score is the number of standard deviations that a given value is above or below the mean. To give a data value a Z-score, well, if that data value is from a sample, you can calculate its Z-score by, you take whatever that data value is, then you'll hit minus on your calculator. You'll enter the mean from the sample, X bar, and you'll divide it by the standard deviation. When you hit enter, it's going to give that data value what's called a Z-score. Similarly, if you're working with the entire population of data, you can find a Z-score of an individual data value by type in that data value, hit the minus sign, type in the population mean, mu, and then divide it by the population standard deviation. It'll give that data value a Z-score. Notice that these equations look very similar. This is just from a sample. Same thing, Z-score, but using population. And there's that Z again. Z-scores are 0. Headed this direction, we can have a Z-score of 1. It doesn't have to be whole numbers. It can be in between as well. We can have a Z-score of 0.5. We can have a Z-score of 2. And that Z-score of 2 is actually our cutoff for our usual range. Those usual values contain a Z-score between -2 and 2. And we call those values that are not significant. They're just usual, not significant. It would take a higher Z-score or lower, if you're talking on the negative side, to obtain what we call significantly high values and significantly low values. Those are those unusual ones, the ones further than 2 standard deviations away from the mean. So if you have a Z-score of, let's say you're out here, Z-score of, this might be a Z-score of -3 let's go with 4. A Z-score of -3.4 would be considered a significantly low value. A data value having a Z-score of, let's go somewhere here. Let's go like here. So if a data value has a Z-score of positive 2.3, that data value would be considered significantly high. Any data values with Z-scores greater than 2 or less than -2 would be considered significant. They are more than 2 standard deviations above or below the mean. Let's use an example to talk about it more. The mean of a data set is 374.92. Its standard deviation is 105.19. And we're asked, well, what is the Z-score for a data value in that set of 327.83? So we're going to take that data value, X, that'll be our 327.83. We're going to subtract out X bar. X bar is the mean. That's right here. This is X bar, so we'll hit minus this. After we do that subtraction, then we'll hit the division sign, and we'll divide by the standard deviation, which is right here, 105.19. That'll look like this. Oops. $327.83 less. So this is the data value we're interested in. We're trying to find its Z-score. So we subtract it from the measure of center called the mean. whoops, 4.92, and then divide by standard deviation, 105.19. And we get a z-score of negative 0.45. That is not unusual, okay? We were asked to round to the nearest hundredth, so we did 2 decimals. And then we were asked, is that data value unusual? The answer is no. That data value would not be unusual. We would need that answer, that z-score, to be smaller than negative 2 or greater than positive 2 for it to be considered unusual. And ours is not. Negative 0.45 is in the usual range. Let's try another one. Mario's weekly poker winnings have a mean of 323 and a standard deviation of 50. Last week he won $177. A, how many standard deviations to the nearest hundredth away from the mean is that? Okay, to answer that, how many standard deviations away from the mean, that's the same thing as find the z-score. So our z-score here would be, we take our calculator out, we type in the data value that we're trying to find the z-score for, so $177, then hit minus, and type in the mean, that's $323, hit enter. After you do that subtraction, divide by the standard deviation, which is 50, and that will give us, let me make that go away for a second, that'll give us 2.92. Type that in, it's actually, sorry, negative 2.92. So this 177 has a z-score of negative 2.92. The question, though, was how far away from the standard deviation is that? So we would answer it like this. $177 is 2.92 standard deviations, and we say the word below the mean. Why do we say below? We say below because our z-score was negative 2.92. That's unusual, right? That would be considered statistically significant. Oh, which is exactly what they're asking us. Is that unusual for Mario to win $177? The answer is yes, because 2.92 is not within 2 standard deviations of the mean. Last topic in this section is on boxplots. In a boxplot, each quartile contains a quarter of the data. So 25% of our data. What is a quartile? Here we have a minimum data value of 4.5. Quartile 1 has a data value of 35. So this right here is a quartile. It has a median of 68, this set of data. So this is our second quartile. Quartile 3 has a value of 113, so this right here would be considered the third quartile. And this set of data, which wasn't provided to us, we're just told it has a maximum of 225, so this would be the fourth quartile. Each one of these quartiles contains 25% of the data. Notice that this last one, this fourth quartile right here, is bigger. Greater distance between quartile 3 and the maximum. That means that the 25% in this quartile here, it varies more. It has a longer distance. So on a number line, it would take up from here to here, and those values, 113 to 225, vary more than data values, for example, here, 4.5 to 35. See, it's a shorter distance right there. Normally distributed data, for example here, heights from a simple random sample of women, would have each of the 4 quartiles approximately the same distance. And that might shed some light, if you were wondering, on why the range rule of thumb was using division of 4 to get an approximate standard deviation. bell-shaped curve over top, if you will, okay? Versus skewed data. Skewed distribution on a box plot would look something like this. If it was a bell-shaped curve, as we know, would have a skewer like this to the side. So an example of skewed distribution: salaries in thousands of dollars of NCAA football coaches. Not much variance in the lowest quarter of coaches. A little bit more variance in the second highest paid quarter of coaches. More variance, and then that top paid 25% of coaches varies quite a bit in their salary. A modified box plot will identify if there are any outliers. So instead of taking it from here, it will cut off at some point, and then the outliers will be represented by these dots here. You can have data that doesn't have any outliers. This particular set of data, it's on pulse rates, has 2 high outliers. There could also be 1 down here as a low. There could be 2 down here as a low. There could be a 3rd up here as high. But those outliers would be represented by dots if we are constructing what's called a modified box plot. We are going to construct our box plots by using StatCrunch. So we will open the data in StatCrunch, and then we're going to go to the menu Graphs. We're going to select the type of graph that we're interested in. So first of all, we're going to be practicing with box plots. We're going to select our column/variable. We're going to click select the horizontal option, and then we'll hit compute. Here we have our Verizon data speed times in megabits per second, but we have some additional data values this time. We've got up to 20 data values. Let's take these 20 data values and construct a box plot. Look at your notes. What does it say to do? Menu, graph. Look at your notes. What does it say to do next? Choose the type of graph we want, which is a box plot right now. Click on it. What do our notes say to do next? Select our column. And one more thing on our notes. What does it say? Click on draw boxes horizontally. And then we're going to hit compute. That's it. We clicked on columns, we clicked this box here, and then compute. Before we do that though, I want you to notice that the default says use fences to identify outliers. So if there are any outliers, they are going to be identified. So that would be like the modified box plot. You could shut it off if you don't want the outliers identified, but default has it on, so let's leave it on. Compute, and here is our box plot. First quartile, this distribution. Second quartile, a little bit shorter. Third quartile, about the same. It's these upper data speed times that seem to vary more, the top 25% of them. Oh, but notice we do have one outlier. What is that? If you go over it, it says that we have an outlier of 60 megabits per second. Hovering over this will give you some more information. For example, the lower limit, 14.1. Number of outliers is 1. It tells us this point right here would be quartile 1, 22.45. Next, let's see if it gives us just, here we go. Median, 29.4. Let's go to quartile 3. 37.75. This right here would be our upper limit of 55.6, and then our outlier. So if you want what's called, if you're asked to give the 5-number summary, looks like we can go anywhere in this box. And here is, a 5-number summary. If you check here, it starts with the lower limit. That's the first number in the 5-number summary. Then Q1 is the second, median is the third, Q3 is the fourth, and the upper limit, not the outlier, the upper limit is the 5th number in what's called the 5-number summary, should you be asked to provide that. All right. That will end our discussion on Chapter 3, as well as end the material for test number 1. So, test number 1 will be on chapters 1, 2, and 3. You can rewatch these videos to help you study, do the homework in My Lab in Mastering. We have a practice test available in My Lab in Mastering. And I will see you next time as far as the YouTube videos after test number 1 when we start the material for test number 2. All right, have a great day. My name is Jami Emigh, and I will see you next time.